Anyone try this? So the example, I'll go through it quickly and then I'll get on to today's lecture. So this example, two long lines of free charge have equal but opposite charge density of plus minus 0.3 nanocoulombs per meter and are placed parallel to each other with a separation of 1 centimeter. Find the field D, which is the electric density, and then E, the electric field at their midpoints if they sit in free space. So that's the first one. The second one, what are the field at the midpoints if the lines are completely surrounded by a dielectric of relative permittivity 1.8? And what is the polarizations of the dielectric at the midpoint? Okay, so you're going to solve the electric field or electric field density at the midpoint, and you can use Gauss law to do that. Okay, so Gauss law to find out the electric field density, so you need to know what sort of Gauss surface that you want to draw around your diagram. So we want to look at the midpoint, so the best way, so this is a wire, a line of charge. So the best Gaussian surface to draw this will be a cylindrical of a radius r, let's say with a length L. So based on Gauss law, is equals to the charge enclosed, and the charge given is per unit length, which is the density. So we call this rho, and the charge is equals to rho times L. So if this is my Gaussian surface that I draw that have a length L, then the charge enclosed within this surface, the Q in here will be equals to rho times L. Okay, so that will be the charge enclosed. And because the electric flux density and the surface are perpendicular, so the dot products, so the surface and the surface vector and the electric field density are in parallel. Therefore, the dot products can be simplified as D times the surface. And this surface here will be simply equals to the perimeters of the circle times the height. So it's 2 pi r times L. That will be my Gaussian surface A. Okay, so you can find out the electric flux density at the midpoint, and the midpoint R will be D over 2. And then the directions of the electric field. So positive charge is the source. So this is my D for the positive. And then similarly for the negative, we can do the same, draw a Gauss surface, and you can solve and you find that because it's negative, so the electric flux density will be pointing towards the negative charge. So you have another one which is D negative, both pointing in the same directions. Okay, so with all that information, we can now put in the value to solve the electric flux density at the midpoint. Okay, so the electric flux density at the midpoint D will be equals to 2 times lambda over 2 pi d over 2. So remember just now my Gauss law. That's equals to d times A. A is 2 pi r times L. R is d over 2. And this has to be equals to, so I use, okay, let me correct that. So I should have used lambda for the charge density, and that will be lambda times L. And this is for the positive. And therefore d due to a positive charge will be equals to lambda over 2 pi. R is d over 2. If you do the same for the negative, you come out with the same answer. Okay, so d negative is also equals to lambda over 2 pi d over 2. Therefore, the total d, the total electric flux density, is twice this value. Okay, it's 2 times lambda over 2 pi d over 2. And we know what's lambda, we know what's d, and therefore we can calculate the electric flux density. Okay, that's equals to what? 19.1 nanocoulombs. And because this is the electric flux density d, so it is the same whether it is in free space or in the dielectric. And then to work out the electric field, E, we simply divide the electric flux density by the permittivity of free space, epsilon naught. And if you do that, that works out to be 2.16 kilowatts per meter. That will be the electric field if the surrounding area is air. Okay, so we make use of this relationship, D equals to epsilon naught E. Okay, so we can find the electric field, simply divide the electric flux density with the permittivity of free space. So that will be 19.1 divided by, or 19.1 nano divided by epsilon naught, which is 8.845 times 10 to the minus 12. Okay, epsilon naught 8.854 times 10 to the minus 12 farads per meter. Okay. Okay, so that is the solution for the electric field in free space. And then the next part of the question asks, what if we place the two line of charge in dielectric with dielectrics or with relative permittivity of 1.8. Okay, so then we just make use of the relationship D is equals to epsilon R epsilon naught E. So meaning that we're going to divide these results by epsilon R. So this electric field will reduce by epsilon R of the dielectric materials. Sorry?
Go back to the question.
Okay, so the next one is asking what happens at the midpoint if the lines are completely surrounded by a dielectrics of relative permittivity of 1.8. So if you put the line of charge in a dielectrics, the electric field will reduce by 1.8 if the relative permittivity is 1.8. The electric flux density stay the same, doesn't change. It's just the electric field reduced by a factor of 1.8 due to polarizations. And then the next part of the question asks the polarization P of the dielectric at the midpoint. Okay, so this is the electric field with a dielectric, okay, reduced by epsilon r. Epsilon r is 1.8, and therefore it ends up to be 1.2 kilowatts per meter. Polarization is equals to the electric flux density minus epsilon naught E, and that will be epsilon r minus 1 epsilon naught E, and that works out to be 8.5 nanocoulombs per meter square. Okay, right at the bottom here, there's a sentence saying, remember that when the lines are surrounded by free space, everywhere have zero polarizations. Okay, what that means is, if you look at these equations, which means that polarization is equal to 0. Therefore, we have our D is equal to epsilon naught E, and that is the case when we have free space. Or in other words, epsilon r is equals to 1. So if this is 1, therefore this is equals to 0, and therefore P will be 0 if we're in free space. Okay, epsilon r equals to 1 in free space, therefore polarization equals to 0, and therefore D will be equals to epsilon naught times E. Okay, so that is that example that I gave you at the end of the last lecture. That was a while back. I think that was about 3 weeks ago. Okay, so we're going to move on from there, carry on that topic. So we're going to look at the electric flux density and the electric field outside a charged metal surface. So previously we have looked at uncharged surface of dielectrics, and then we have looked at Gauss law. So a plain metal surface, I'll show that in the next slides, on which is deposited a positive free charge of uniform charge density, charge per unit area of sigma. So the unit is coulombs per meter square, so it's per unit area, and therefore is per meter square. So just now the line charge that we look at, we have lambda, that is per unit length. This is coulombs per meter, and that is charge divided by the length per unit length. And here is per unit area, that will be my charge divided by the area, per units area. Both the electric flux density and the electric field are zero inside the metal, and both perpendicular to the metal outer surface. Assume dielectric field dissipates outside the metal so that we can obtain the results appropriate for free space by setting epsilon r equals to 1. Okay, so this is the diagram referring to. So we have a metal surface. There's charge deposited on the surface, and then on the outer surface there's dielectric materials right at the surface interface. So we have dielectrics on the top, charged metal underneath, and we know that the electric field or the electric flux density D, both pointing perpendicular to the surface of the conductors if the surface is positively charged. Okay, so we have source of positive charge, the electric flux density pointing away from the source of the charge, which is a positive charge. And now we can apply our Gauss law. So to apply it, we need a Gauss surface. And the most appropriate surface for this will be a cylindrical, what we call a bean can. Okay, so we draw your Gauss surface here, and this can sit perpendicular to the surface. So allow it to sit on either side of the surface. So this can, okay, is sitting right, or the interface is right at the center of this can. So we have one side on the dielectrics, the other side inside the metal. And then we define, or we can call this surface here, my can surface on the top is A. Okay, so if this area is A, and our charge density on the surface here is sigma, the amount of charge that's confined inside this bean can will be this area A times the surface charge density. Okay, so if I were to draw it in three-dimensional, if I draw a can that has area A, so this is the area on the surface. Okay, so if this is A, this area that is touching the surface is also A. So in this part here, the amount of charge will be sigma times A. That will be the charge inside this area. Okay, do you get that concept? So I have a charge density. So if I want to work out how much charge on a particular surface, will be that surface area times the charge density. In this case here, we put a can, so it will be the surface of the can top times the area, no, times the charge density will give you the amount of charge that confined with that particular area. Okay, so the amount of charge will be basically in this region here, and this region's the amount of charge that's confined inside here, Q, will be my charge density times this area here, A. Okay, that's the amount of charge inside this area, and that area will be the same area as the top of my bean can. Okay, so this charge is only on the surface of the conductors. There is no charge on the dielectrics, whether on the surface of the dielectrics or within the dielectrics. Okay, the charge is only on the metal surface. Okay, so the electric flux that trading through my Gaussian surface is only on the top where the dielectric is. There is no electric flux trading to this surface because that surface is inside the conductor. And we know that electric flux density cannot live within a conductor in a static scenario. So in electrostatics, there is no electric field or electric flux density inside conductor. So this is my metal surface. Therefore, there will be no electric flux inside the conductor. Therefore, no flux is actually trading through this surface. And my cylinder, there are three surfaces. Okay, so my cylinder, there are top surface, bottom surface, and then the surrounding or the curvature surface of my can here, or my bin can. Okay, so only the top, bottom, and the curve. The top we have electric flux that is trading through. Bottom, because it's inside the conductor, so electric flux is 0. And then surrounding is not actually trading through it because it's in parallel to the surface. Okay, so you have the curvature, the flux going in the vertical direction. So there's no electric flux actually trading through the curve of my cylinder or my bin can. And therefore, the electric flux only trade through this surface here on the top. And the rest is 0. Okay, so it's 0 on all other parts except the one that live on the dielectrics on the top. Okay, so as I mentioned, no lines of D trade the curved surface of my Gaussian surface, and therefore we do not have to consider the area, the curvature area, only the area on the top. So applying our Gauss law, the electric flux equals to the closed surface integral d dot ds equals to d times a, because the electric flux density is in the direction of the vector surface S. And therefore we can simply take d times a equals to q, and q, as I mentioned just now, equals to sigma times a. And with that, we find that the electric flux density simply equals to the charge density of the surface. So the electric flux density D is at all points perpendicular to the surface or the metal surface and has a magnitude of D equals to sigma, which is the charge density, and does not depend on whether dielectrics or free space in the presence outside the metal. Okay, so the electric flux density is the same whether you have a dielectric materials right outside the conductor surface or it is a free space. It is the same magnitude, which is equals to sigma charge density. Okay, do you follow so far? No? Yes? So this is Gauss law, applying Gauss law on a surface. Okay, so apply Gauss law on surface. First, you introduce a Gaussian surface. In this case here, we applied a cylindrical surface. Solve your Gauss equation, Gauss law equation, d dot ds, and because it is perpendicular, So we don't have to do the integrations. It's simply equals to d times the area. And that has to be equals to the charge enclosed in that Gaussian surface. And the charge enclosed is equals to Q. Q equals to sigma times A. And if we want to find the electric field, then we simply again apply our relationship D equals to epsilon R epsilon naught times E. Okay, I keep writing these equations. I hope you remember it by heart. Okay, so if you keep looking at the same equation, okay, I should write it down here. D equals to epsilon R epsilon naught E. Okay, so this equation again. So this is the relationship between electric flux density and the electric field. And therefore you can find the electric field via this relationship. And therefore the electric field will be equal to D over epsilon R epsilon naught. If it's free space, what do? We set epsilon R equals to 1. Okay, and we'll find the electric field in free space. If it's a dielectric, then we need to know what is the relative permittivity of the dielectric, epsilon R. Okay, so here is that usually it is sufficient to quote just the field magnitudes and state that the vector is pointing perpendicular to the surface. So in this case here, our example, we have a flat surface. So the direction of the vector field of this is just perpendicular to this surface, and then we work out that the electric flux density will be equals to sigma, and then the electric field will be sigma over epsilon R epsilon naught. And then the directions of the field depending on the charge. If it's positive, it will be pointing away from the surface. And if it's negative, it will be pointing towards the surface. Because we know that positive charge is a source, negative charge is a sink. The next part, okay, so that is finding the electric field on outside a conducting surface. Any questions on that? So that's directly applying Gauss law. So we have looked at Gauss law, applying it on a line of charge. And then here we look at the applying Gauss law on a flat conducting surface. And we know that the electric field or the electric flux density is equals to the charge density on the surface. So if this is conductor, if I want to work out the electric field, we know that the electric field will be pointing perpendicular to this surface, and the magnitude will be the charge density divided by epsilon R epsilon naught, and that will be the electric field on this surface. The other thing you need to take note is that in a flat surface, it doesn't depend on the distance. It just depends on the charge density. Unlike in point charge, the further you go away, the electric field changes with distance. But here, it doesn't. Okay, it just depends on the charge density of the conducting plate. So the next part of this is to look at the boundary conditions for electric flux density at interface carrying a finite free charge. So very earlier on, we have looked at boundary condition. If you have one dielectric, another dielectric at the interface, we said that D is the same from one materials going to the other materials if D is perpendicular to the boundary. So that is uncharged Okay, so that boundary have no charge. So here we're going to move on. If you said that the boundary actually has some charge on it, what will happen to our D? Okay, without charge we know that D1 equals to D2. What we have looked at early on. If there's no charge, D1 equals to D2. But now at the interface, we have some charge in the interface, which is Q equals to sigma times A. So this surface has a charge density of sigma, and therefore the charge will be sigma times the area of interest. Okay, so we can modify our boundary conditions by applying what we have known. Okay, so there's a free charge at the boundary. So again, we can apply our Gaussian surface, draw a Gaussian surface at the interface. So we know that there is the electric flux density D1 in one materials, D2 in the next materials, and then now we have some charge in the interface. So looking at this, the flux trading through this surface, that will be the difference between D1 and D2 times the area A. And that has to be equals to the charge confined inside our Gaussian surface. So the electric flux into the Gaussian surface is D1A, and the flux going out is D2A. Okay, so we have the flux going into here, D1A, and then the flux going out here is D2A. And the difference of that has to be equal to the charge enclosed in that surface. So you have electric flux going in, and then electric flux coming out. Okay, so the difference between D2 minus D1 or D2A minus D1A, according to Gauss' law, that has to be equal to the charge enclosed. And the charge enclosed will be equal to Q equals to sigma times A. So if we put all this together, we have the equations D1 or D2 minus D1 times A, that will equals to sigma times A. And therefore we end up with this equation here, D2 minus D1 equals to sigma if there is a finite charge at the boundary. Okay, so go back to our original boundary condition where there is chargeless, meaning that sigma equals to 0. So if there is no charge, then we have sigma equals to 0. Therefore this equation ends up with D2 equals to D1, which is our original boundary conditions for a chargeless conditions. Okay, that is what we have talked about very early on, about how the electric flux density go from one medium to another medium. If it's perpendicular, then we have D1 equals to D2. Okay, so if there's no free charge on the boundary, D2 equals to D1, which is the boundary condition we introduced previously in the previous topic that I talked about boundary conditions. If there's free charge on the boundary, then the discontinuity in the perpendicular components of D is equal to the free charge surface charge density. Okay, so if there is charge, then the difference between the electric flux has to be equals to the charge density. Okay, so this discontinuity arises since the free charge acts as a source if it's positive, or sink as a negative of D at the boundary. Okay, so going back to this diagram, so if there is charge, I got my D1 going in and then D2 coming out. So if it's a positive charge, then this positive charge acts as a source to provide extra electric flux if it's positive. Okay, so if it's a negative, then it acts as a sink. Then you have electric flux going in the opposite directions to reduce the amount of flux that actually going in from D1. Okay, so that is the scenario if you have a charge boundary. If there is no charge boundary, then whatever the electric flux density or electric flux going in has to be equal to the electric flux going out. Okay, so if there is no source or sink at the boundary. So that makes sense. Whatever I put in here, it has to come out the other side. Okay, so if you have extra charge here, whatever I put in here, there will be extra coming out here. Okay, because there are extra charge inside my boundary. Or it reduces if there is a sink. Okay, so if there's a negative charge, then you have a sink at the boundary. Okay, here's an example. A charge Q is distributed on the surface of a solid metal sphere of radius A. What is the electric field at the surface of the sphere if it sits in free space? So you think of a charge ball. Okay, if you have Q charge equally distributed on the surface of this metal ball, so I ask you, what is the electric field at the surface of this metal ball? Okay, so here I'm just going to go through it so you don't really have to solve it. Okay, so on the surface of the sphere, the mutual repulsion between each of the individual charges that make up Q ensure that the charge spreads out uniformly. Okay, so with conductors, we know that the charge will distribute evenly on the surface, and therefore the charge density sigma will be equal to Q over 4 pi r squared. 4 pi r squared is the surface area of a sphere. Okay, so the surface area of the sphere is 4 pi r squared. The sphere has a radius of A, that will be 4 pi a squared. Okay, that will be the charge distributions. So the charge density sigma will be equal to Q divided by the area. Both D and E points radially outwards at all points because there's a surface. We know that the electric flux density and the electric field point perpendicular to a conducting surface. Okay, so because this curvature is always pointing perpendicular, so it will be pointing radially outwards from the metal ball. Okay, and then from equation 7a, I repeat my 7a here, which is my Gauss law. The integral d dot ds will be equals to d times a equals to q, and that will be equals to the charge density times a, and therefore d is simply equals to the charge density. And we know that the charge density is equals to Q over 4 pi r squared. R is A, so that will be Q over 4 pi a squared. And therefore the electric field will be equals to Q over 4 pi epsilon naught a squared on the surface of my conducting ball. Okay? So now go back, think about if I have a point charge at the center of this ball. Okay, so point charge. So point charge based on either Gauss law or Coulomb's law. If you go via Coulomb's law, the electric field is also equal to Q over 4 pi epsilon naught r squared. So at the surface, there will be also A. Okay, so that will be equal to Q over 4 pi epsilon naught A squared. If I have a point charge Q at a distance of A, the electric field here is equal to 4Q over 4 pi epsilon naught A squared. Okay, which is the same as this. This is on the surface of my metal sphere. This is point charge. Okay, can you see the similarity of that? So they are both the same. So if I have a sphere with a charge density or with Q charge distributed over the surface, is exactly the same as if I have a point charge at the center of the sphere. The difference is that if I have point charge, I have electric field at every point away from that point charge. Okay, so at every distance here I have electric field. But in a metal sphere, the electric field is only on the surface and away from the surface. Inside the metal sphere, we said that the electric field is zero because electric field cannot live inside a conducting surface. Okay, so that's the difference. Okay, so inside here, if it's conducting sphere, electric field here is equals to 0. If it's point charge, then you have finite electric field that changes with the distance. So this interesting result tells us that the field on the surface of a metal sphere look like those that would result if the surface charge Q was placed at the center of the sphere. Inside the metal sphere, the field must be 0 everywhere. That's what we have said earlier on. Inside a conductor, electric field or electric flux density cannot live with it within the conductor. So it turned out that the field at a radial distance r greater than A from the center of the sphere look like a point charge Q placed at the center of the sphere. Okay, so if the example that we have just now, we have a sphere. The sphere has a charge density equals to Q over 4 pi A squared. So it looks as if that this is a point, this is equivalent to a point charge of a value Q sitting at the center of the sphere. Okay, for any point outside the sphere. If I want to find E at this point, it will be just this distance here, R, and this will be equal to Q over 4 pi epsilon naught R squared, which is the same as my point charge right at the center of the sphere. Okay, that was the what it's trying to illustrate here. Okay, so try showing this result using Gauss law. You can then also show that the field inside and outside of a hollow charged metal sphere are exactly the same as the sphere was a solid. Okay, so if this is a sphere, okay, we know that the charge is going to distribute outside the sphere. So if I draw a Gaussian surface inside, what's the charge enclosed in this Gaussian surface? Okay, so charge distributes on the surface outside. Okay, so no charge inside here. So if I draw a Gaussian surface here, then Q will be equal to 0. Okay, so inside my metal sphere, Q will be equal to 0 because the charge distributes at the outside. If I draw a Gaussian surface outside, the charge enclosed will be Q because the whole surface has Q distribute over it. So the total sum of all the charge will be Q. Okay? So using Gauss' law, you can find that E will be equal to Q over 4 pi, or D will be equal to Q over 4 pi R squared. Okay, so 4 pi R squared will be my Gaussian surface, or my D times A equals to Q. A is my Gaussian surface, which is 4 pi R squared. Okay, and therefore D will be equal to Q over 4 pi R squared. Inside the sphere, Q is 0, therefore D is also equal to 0 inside the sphere. Similarly, if we have a hollow conductor, again the charge distributes at the outer surface. Okay, so if I draw a Gaussian surface inside here, inside the hollow bit, Q is also equal to 0, therefore D is also equal to 0. Okay, so this leads to what we call a Faraday cage. So what's a Faraday cage? Okay, I'll give you 5 minutes break, and then we'll come back to look at what is a Faraday cage.
Still upload the video. No more.
I will try to do that, yeah. I just haven't got time
So
to do
I just find your lecture is a bit too long, and I just want to
it. Okay, I will try to,
get the
yeah.
video. And
I meant to do that, but I haven't got time to do it. Yeah, but I will make sure that I put it up before the exam.
yeah, hopefully early lah.
Yeah, I'll try to do it earlier, yeah. Okay, we'll continue. Okay, Faraday cage. Sometimes it is necessary to protect certain types of sensitive equipment from damaging effect of electrostatic charge. Okay, so sometimes a lot of equipment is very sensitive to electrostatics. So electrostatics can actually be hazardous to some of the electronics equipment. And to protect equipment from this, we have something known as a Faraday cage. And this is discovered or recognized by Michael Faraday. And he found out that you can screen electrostatics by putting them in a metal enclosure. Okay, so suppose we bring a charged Q to the neighbor of a shield. So if I have a hollow sphere, okay, my conducting ball hollow inside. So if I bring a charged Q to this conducting ball, then the electrons will draw towards where Q is and leave behind a positive charge on the other side. But overall, this hollow conducting ball is still neutral. The charge redistribute at the outside, but inside this ball where the hollow bit is still no charge. Okay, so if I draw my Gaussian surface inside there, it is still, Q is still equal to 0, and therefore there's no electric charge density or electric field inside these hollow bits of my conducting ball. And therefore if you put any equipment inside there, whatever happened outside, it will not have any influence on what is inside. So this is known as a Faraday cage. Have you come across the terms called EMP? Electromagnetic pulse. I'm sure if you look at if you watch any sci-fi movie or anything like that, you hear about EMP destroy all the electronic equipment and everything. Okay, so if you have your equipment inside this Faraday cage, then EMP will not be affecting you. Or if you live inside this Faraday cage, then you'll be fine as well. Okay, so that is what is Faraday cage is about. Okay, so if you have conducting screens fully enclosed, anything inside it will be protected against electromagnetic interference or electromagnetic pulse as well. Okay, so that is what Faraday cage is. So the external charge induced charge on the surface of the conducting sphere as shown, since charge is mobile on the surface. And if the sphere is Earth and the external charge is positive, then negative charge is induced on the outer surface of the sphere. So if I ground this, if I earth this, what happens is that electrons will flow and neutral out all the positive charge. I end up with the whole sphere become negatively charged. But even then, what is inside is still zero. Okay, so because this is conductor, anything inside here, there's still no charge inside. Whether I earth it or not, inside here, Q is always equal to zero. Okay, and therefore there's no electric field or electric flux density inside that region. Okay, so the crucial things, E and D must be zero inside the hollow, and so the effect of the surrounding sphere is to screen any external electrostatic field from its inside. So anything happen on the outside have no influence on the inside of the hollow bits of the sphere. Okay, so that is what Faraday cage is. The next bit is a differential form of Gauss law. So previously we talked about Gauss law, which is my equation 5, is in the integral form. So the closed integral d dot ds is equals to charge enclosed in my Gaussian surface. But sometimes it is useful to express it in a differential form. Okay, so this is in integral form, and we're now going to look at how we can put it into a differential form of Gauss law. So suppose we have a region of space that has a free charge per unit volume. So we use the sign rho. Rho is Q over the volume, so per unit volume, where for now we assume that the charge density is a function of position x. Okay, so if you think of a free space, so it's just changing in one direction, constant in the other two dimensions. Okay, so we assume it's constant in the y and z directions, only changes in the x directions. Okay, so this is the scenario. So this is my x directions. Okay, so in this case here, this is my x directions. So in my vertical directions is constant. In my horizontal or pointing out from my screen, that also constant. The charge doesn't change. The charge changes in the x directions. Okay, so if I were to put that into three-dimensional, maybe I can draw this. So meaning that, okay, something like this. Okay, so in my y and z direction doesn't change, it just changes in the x direction. Okay, so this is my area A. This is A, and therefore the flux, my electric flux going into this volume, so you can think of this is infinitesimally small volume with a thickness of dx, got an area A but very thin, dx. So what's going in and then what's coming out. So at this point here, if this is my x, here will be x plus dx. Okay, so if I plot this on my x-axis, at this point here is x, then here a small increment of dx, that will be x plus dx. The charge doesn't change in y and z directions, and this here I have an area A. Okay, so the electric flux trading through this surface will be d with a function x times A, and then coming out will be d small increment x plus dx times A. Okay, do you follow so far on this diagram? Okay, so think of it as a volume. Okay, let's say rectangular volume, very tiny thickness of dx with an area of A. Okay, so if I draw, let me draw this. So you can think of it as x, y, and z. So if I want to calculate the volume, this is my area. A will be y times z. Then the volume will be A times x. Right? So if I want to calculate this volume, so if my x is very small, I call it my dx, then this will be A dx. Correct? The volume here. So sometimes we call this dV. Okay, so remember previously I talked about the rectangular coordinate system. I have dV equals to dx dy dz. Okay, it's just that now my y and z is a finite area, so it will be A dx. Okay, in this example, so from superposition that the field D, the electric flux density, and E is pointing along the x directions and perpendicular to the surface or the Gaussian surface, which I call my surface area A. Okay, so the electric flux density and the electric field will be pointing perpendicular to this surface here. Okay, so this is in the x direction. And the charge regions is made up of a finite number of flat sheets of charge with the plane perpendicular to x-axis. And the field produced also in the x-axis. Okay, so we no longer assume that the field magnitudes are uniform, unlike in previous example on the flat surface, I said the charge density is equal to sigma. That is a uniform charge distribution. So now the charge distribution changes with the x directions. Okay, so we expect them to be a function of x. So to work out the charge, okay, so we said that charge is equals to Q over A, not over V, volume. And we said that the volume is equals to A dx. Okay, so that is my volume that I mentioned just now, my volume here. V is equals to A dx. Okay, so this is the volume. And therefore the charge Q will be equals to rho times A. Sorry, keep writing A. Should be V, and that will be rho, which is a function of x, A dx. Okay, so there is a charge enclosed in that volume. And then the net flux going through, we have one going in and one coming out, and therefore we take the difference. So back here we got D going in and then D coming out. So the net D inside here will be the difference between the two, and therefore we have dx plus dx times A minus dx times A, and that has to be equals to the charge enclosed. So this is a very similar problem as our charge surface interface. Okay, just now when we look at the charge interface of D1 going in and D out coming out, and then this interface has a charge density. So this is a very similar problem. Okay, so we have, so in the previous one we have D1A or D2A minus D1A equals to the charge at the interface. Here we have D at the distance of x plus dx times A minus D at the distance x times A equals to A, now equals to the charge density times the volume. And this part here, okay, is the change in the electric flux density over a small distance. So if we divide that by that small distance, that becomes a derivative. Okay, so I'm sure you learn about dy dx. It's a limit of the infinitesimally small dx becomes 0, and therefore it becomes dy dx. Okay, so we divide this by dx, and then times it with dx. Then this bit here, if I take my A out, okay, I'm just making it very messy now. So if I take my dx plus dx minus dx, okay, so here with the limits, so normally we put this delta x and then divide by delta x with delta x limits to 0, and this becomes dd over dx, and that is what we normally learn about differentiations. Okay, oh dear, you can't see that. Okay, just trying to recall your understanding when you studied about dy dx as a function. Okay, so that is, you may or may not come across this when you study in maths about differentiation equations. So the differentiation is when one direction is a small change of delta x. So you find the difference between the functions of that two different points of delta x. Divide by delta x when delta x become very small, limits to 0, and that way you have your differentiation df by dx. Okay, so the same thing here, we make d plus dx minus x over dx, and that is our dx over dx. That's our differentiation equation. And then because we divide one side with dx, we have to multiply it so that they are the same thing. And therefore we end up with this equation here, and that's my equation 9, which is my Gauss law in a differentiation form, or differential form of Gauss law. Okay, so we have the integral form. So this is another way of writing Gauss law in a differential form. And then to work out the electric flux density, we simply integrate over the flux density, rho, against the dx, and we can work out what is the electric flux density. Okay, so what I'm doing this just to show you where this is leading to. This is leading to something known as the Maxwell equations. Okay, so just now we see that it changes with x directions. So if it changes with y and z directions, then we have del d in the x direction over dx plus del d in the y direction over dy, and then del d in the z direction over dz will be equals to the charge density. And then we recall what we have talked about, the del function. The del function is del over del x, del over del y, del over del z. So it's a dot product, d dot d equals to sigma. Okay, so this is known as the Maxwell equations. So this is called the divergence of the electric flux density. So if you remember back my very first lecture, I talked about vector, talked about divergence. What is divergence? The divergence okay, anyway, that is the don't know what's happening here. Okay, so the divergence. So remember in my lecture about vector, I talked about divergence is talking about whether there is a source inside a bubble or there is a sink inside the bubble. Okay, so here is the divergence of the electric flux density. So the divergence is equals to the charge density. So here, if I draw my Gaussian surface, inside my Gaussian surface there is no charge. That means there is no source or sink, and therefore my divergence will be equals to 0. Okay, so if there is charge inside the bubble that I draw my Gaussian surface, then there is a source or a sink. Therefore my divergence is finite, which is this equation here, which is my Maxwell equation. The divergence of the electric flux density is equals to the charge density of the Gaussian surface that I draw. So which means that there's either a sink or a source inside the bubble or the Gaussian surface or the cross surface that I draw. Okay, so this all leads back to the vector algebra of divergence. So the divergence of the electric flux density is equals to the charge density.